Welcome to Week 5 of Fundamentals of Python and Machine Learning. In this lesson, we are covering Chapter 5, getting started with Scikit-learn and Machine Learning. During the previous chapters, we built the data foundation needed for machine learning. NumPy helps us work with numerical arrays, Pandas help us organize and manipulate tabular data, Matplotlib and Seaborn help us visualize patterns and relationships. Now, we are ready to begin training machine learning models. Scikit-learn provides the tools needed to prepare data, select models, train those models, make predictions, and evaluate the result. This chapter represents an important transition. We are moving from understanding data to using data to train a model. By the end of this chapter, you should be able to explain what Scikit-learn is and what is widely used in machine learning. You should be able to load datasets included with Scikit-learn and recognize the features, labels, descriptions, and target names provided by those datasets. You will also learn how to generate synthetic datasets for regression, classification, and clustering experiments. You should understand the basic machine learning workflow, including separating features from labels, splitting data into training and testing set, fitting a model, making predictions, and evaluating the results. Finally, you will learn several important data preparation techniques, including handling missing values, removing duplicates, normalizing numeric features, and identifying possible outliers. Before using Scikit-learn, it is important to understand how this chapter connects to everything we have already studied. NumPy tells us how numerical information can be represented in arrays. Pandas tells us how rows and columns can organize real-world records. Visualization helps us examine patterns, distributions, relationships, and usual values. Scikit-learn now uses prepared information to train machine learning models. A model does not replace NumPy, Panda, or visualization. Instead, those tools work together. Panda might organize the dataset, NumPy might represent the numerical values, Matplotlib might help us understand the data, Scikit-learn then uses the prepared features and labels to train and evaluate the model. Implementing a machine learning algorithm from scratch can require a strong understanding of mathematics, statistics, optimization, and computer programming. Scikit-learn provides ready-to-use implementations of many common machine learning algorithms. It supports tasks such as regression, classification, clustering, pre-processing, model selection, and model evaluation. Instead of programming every mathematical step manually, we create an instance of a model and uses a consistent set of functions to train and evaluate it. This allows us to focus on a large workflow. What problems are we trying to solve? What data do we have? Which column should we become features? What should the model predict? How well does the model perform? Scikit-learn makes the implementation easier, but we still need to understand the data, select the appropriate model, and interpret the results responsibly. One useful feature of Scikit-learn is that model follows a consistent pattern. First, we create an instance of the model. Second, we call it fit method, using training features and training labels. The word fit means that the model is learning patterns or parameters from the training data. Third, we call the predict method to produce prediction for new feature values. Finally, we evaluate the model using a score or another appropriate metric. The specific algorithm may change, but this general structure remains familiar. Create the model, fit the model, make predictions, evaluate the results. You will see the pattern repeatedly through the remaining of the chapters. Before selecting a model, we need to identify the type of problem we are solving. Regression predicts a numerical value. Example includes predicting a house price, temperature, future demand, or student score. Classification predicts a category. Examples include spam or non-spam, pass or fails, approve or deny, or one category among several possible categories. Clustering is used to discover a group of within unlabeled data. For example, a business may group customers according to similar purchasing behavior. Scikit-learn includes algorithms and datasets for each of those problem types. Choosing the correct type of model begins with understanding what kind of result we need. A machine learning model cannot learn without data. One common challenge is finding datasets that are appropriate for experimentation. Scikit-learn includes several built-in datasets that can be loaded directly from Python. The datasets are useful for learning because they are already organized and documented. We can also obtain data from public repositories such as Kaggle and the UCI Machine Learning repository. In a workplace, data may come from databases, spreadsheets, application logs, surveys, or information system. Finally, sklearn can generate synthetic datasets. Synthetic data is created programmatically and can help us understand how algorithms behave under controlled conditions. The source of the data may vary, but the dataset must be still inspected, understood, and prepared before training a model. Scikit-learn provides several standard databases through the Scikit-learn Datasets module. These datasets are commonly used for learning, demonstration, and comparison between algorithms. The iris dataset contains measurements from different types of iris followers. The breast cancer dataset contains diagnostic measurements that can be used for classification. The diabetes dataset can be used for regression. The handwriting digits dataset contains a small image representing numbers. Built-in database allows to begin experimenting without first downloading and cleaning the separate file. However, we should still inspect the documentation and understand what each feature and target represents. Many Scikit-learn datasets are returned as an object called a bunch. A bunch behaves similar to a Python dictionary and provides name properties that describe the dataset. The text property contains with greater description. The data property contains the feature values. The target property contains the labels and expected output. The target name property contains the names associated with numerical target values when those names are available. Some datasets also provide feature names. Understanding test properties is important because we should never train a model without knowing what the input value and labels represent. A dataset is more than an array of numbers. Every row and column should have a meaning. Let's look at a simple example using the iris dataset. We begin by importing load iris from Scikit-learn datasets. Then we call the function and store the result in a variable called iris. The result values are available through iris.data. The target labels are available through iris.target. We can assign the features to a variable called capital X, and the labels are to a variable called lowercase y. This naming pattern is common through machine learning. The dataset also provides features names and target names, which help us understand the meaning of the numerical values. Before training a model, we should inspect those names, examine the shape of the data, and understand the problem represented by the dataset. Built-in datasets are useful for practice, but real projects often require external data. Kaggle provides datasets created and shared by a large community of data scientists and organizations. The UCI Machine Learning Repository also contains many datasets commonly used in research and evaluation. Examples may include student performance, automobile efficiency, census information, product prices, or sensor measurements. When selecting a public dataset, we should review its description, source, column, definition, licensing, and node limitations. We should also ask whenever the dataset is appropriate for the problem we want to study. A dataset being publicly available does not automatically mean it's accurate, complete, unbiased, or suitable for every use. Sometimes we don't need real-world datasets. We might want a control dataset that helps us demonstrate how a particular algorithm works. Scikit-learn provides functions that generate synthetic data. The MinMaxScaler function generates data with a numerical relationship that can be used for regression. The makeBlobs function generates a group of cluster of points. The makeCircles function generates points of arranged in two circular groups. Synthetic datasets are useful because we control their size, shape, amount of noise, and random seed. This makes them useful for teaching, experimentation, visualization, and testing algorithms. The MakeRegression function creates synthetic data for a regression problem. In this example, we request 100 samples for one feature. The noise parameter adds variation so the point does not fall perfectly on one line. The random stem allows us to reproduce the same generated dataset later. The function returns x and y. X contains the feature values, y contains the numerical target values. When plotted, the point might appear around an approximate straight line relationship. This provides a useful dataset for learning how linear regression finds a line that best represents the pattern. The makeBlock function generates group of data points. In this example, we create 150 samples organized around 3 centers. The results can be displayed as scatter plot with 3 possible clusters. This kind of dataset is useful when studying clustering algorithms, such as k-means. The generated j-values identify the cluster used to create each point. Although an unsupervised clustering model will normally attempt to discover the groups without using those labels during training. This is a good example of how generated data can help us compare an algorithm results with a known structure. The makeCircle function creates a dataset with two circular groups. One group forms an outer circle, another forms an inner circle. This pattern is important because a simple straight line cannot easily separate the two groups. The dataset helps us demonstrate why different algorithms are needed for different data shapes. An algorithm that performs well with a straight boundary might not perform well with circular data. This is a major machine learning lesson. The example and structure of the data should influence the model we choose. There is no single algorithm that is best for every problem. Let's bring the chapter concepts together into a basic machine learning workflow. First, define the problem and the result you need. Second, obtain an appropriate dataset. Third, expand and clean the data. Fourth, identify the input features and the target value label. Fifth, split the available data into training and testing sets. Sixth, perform the required pre-processing, such as scaling numerical features. 7. Create and feed the model using the training data. 8. Use the model to make predictions. 9. Evaluate those predictions using test data the model did not use during training. Finally, save, communicate, or deploy the model if its performance and intended use are appropriate. Machine learning is not only the feed function, it's the entire process. Scikit-learn models commonly receive two main inputs. Capital X contain the features, lowercase y contain the target or label. Suppose we want to predict the student final score. Hours studied and attendance might become input features. The final score becomes the numerical target. Each row in X must correspond to the same row in Y. In other words, the feature values for the first student must match the first target value. It is also important to understand the shape of the data. X normally two-dimensional, with rows and feature columns. For many supervised learning problems, is one-dimensional, containing one target value for each row. We should not train and evaluate a model using exactly the same data. If the model is tested only on information it already saw during training, the result might appear better than its actual ability to work with new data. Instead, we split the dataset. The training set is used by the model to learn. The testing set is held inside and used later for evaluation. In this example, 20% of the data is reserved for testing. The random state makes the split reproducible. It is also important to split before learning preprocessing values such as minimums, maximums, means, or standard deviation. The test should remain separate from the training process to help us evaluate how the model might perform when it receives new unseen information. The chapter introduces scikit-learn modeling through their linear regression. Linear regression models the relationship between a numerical target and one or more numerical features. With one feature, we can visualize the model as a straight line. The line attempts to represent the overall relationship between the feature values and the target values. For example, we might examine the relationship between hours studied and final score. The individual point will not normally fall exactly on the line. The goal is to find a line that produces the smallest overall prediction error, according to the method used by the model. Once the line is learned, it can be used to estimate target values for new feature inputs. To train linear regression model, we import the linear regression class. Then we create an instance and store in a variable called model. At this point, the model exists, but it has not learned anything. We train it by calling model.feed, xtrain, ytrain. The feed model examines the relationship between the training feature and the training target. It calculates the coefficient and intercept the define of the filter linear relationship. After the feed operation completes, the training model can make predictions. These two-line patterns appear simple, but it represents the mathematical training process implemented by Scikit-learn. After training, we can use the model predict method. To evaluate the model, we usually pass X tests and obtain one prediction for each test row. We can then compare those predictions with the actual values stored in y-test. We can also make a prediction for a new input. Notice that a single feature value might still be written inside two sets of brackets. The outer structure represents the rows or samples. The inner structure represents the features for that sample. The model returns a prediction based on the relationship it learned from the training data. A prediction is an estimate, not a guarantee. Its usefulness depends on the data quality, the suitability of the model, and the evaluation result. A fitted linear regression model provides its learned coefficient and intercept. The coefficient represents the expected change in the prediction when the feature increased by 1 unit, while other included features remain fixed. With one feature, the coefficient acts like the slope of the line. The intercept represents the predicted y value, then the feature value is 0. We can access these values through model.coef or model.intercept underscore. These properties help us inspect the relationship learned by the model. However, interpretation still requires context. A mathematical relationship does not automatically prove that one variable causes another. The model describes a pattern found in the training data. A residual is the difference between an actual value and the value predicted by the model. If the actual score is 90 and the model predicts 86, the residual is 4. Some residuals might be positive and some others might be negative. If we simply add them together, they might cancel each other. The residual sum of squares, or RSS, solve this squaring each residual and the adding the square values. Squaring also gives larger errors more influence. A smaller RSS generally means that the predictions are closer to the observed values for the dataset. However, RSS depends on the scales and number of observations, so it's not always convenient for comparing unrelated datasets. This is one reason we also use other evaluation measures. For linear regression, the model scores method returns is the R-square value, also called the coefficient of determination. R-square compares the fitted model with a simple baseline based on the average target value. The formula is 1 minus residual sum of squares divided by the total sum of squares. A value of 1 indicates that the prediction perfectly matched the observed test value. A value closer to 0 indicates that the model explains less of the variation in the test target. R-squared can also be negative when the model performs worse than the baseline comparison. A high score should not be big within isolation. We should also examine the datasets and residuals, the test set size, possible leakage, and whatever the model is appropriate for the real problem. Training a model might require time and resources. If the model has already been trained, we might want to save it and load later, instead of repeating the training process every time. This is called model persistence. The chapter discusses pickle and joblib. Joblib is commonly used to save Scikit-learn models and objects that contains NumPy data. We can save the model to joblib dump and load it with joblib load. When we load it, we recover the trained object and can use it to make predictions. Model files should be handled carefully. Only load model files from trusted sources because serialized files might execute harmful code when opened. We should also record the software version and pre-processing the steps required by the model. Real-world data readily arrives are ready for machine learning. It might contain missed values, duplicate rows, incorrect entries, inconsistent format, or extreme observations. Machine learning algorithm does not automatically understand whenever a value is a mistake. It learns from the information we provide. If the input data is inaccurate or poorly prepared, the model might learn misleading patterns. Data cleansing is therefore part of the model development, not a just-related task. Before removing or replacing anything, we should understand what the values mean, how they were collected, and why the problem occurred. Cleaning decisions can affect the final model and the people or process influenced by this prediction. Pandas often represent missing numerical values as not a number. One option is to remove rows containing missing values with dropNav. This might be reasonable when only a small number of records are incomplete, and removing them will not distort the dataset. Another option is to replace the missing value. For a numerical column, the chapter demonstrates replacing missing values with the column mean. Neither approach is automatically correct. Dropping too many rows might remove valuable information. Replacing values with a mean might reduce variation and hide important patterns. In a formal machine learning workflow, any replacement value should be learned from the training data and then applied to the test data. The test set should not influence the values used during training. Duplicated records can cause some observations to have more influences than intended. Pandas provide a duplicated method to identify repeated rows. Using keep equal to false marks every occurrence of a duplicated row, which can help us inspect the records before deleting anything. The drop duplicate method can remove repeated rows while keeping the first occurrence. We can also use the subset parameter to find which column determines whenever records are duplicates. This is important because two rows may contain similar values without representing the same real-world observation. Before removing duplicates, confirm that uniquely identify a record. A repeated transaction may be an error, or it may be two legitimate transactions with the same amount. Features may use very different numerical ranges. For example, age might range from 18 to 70, while annual income may range from 20,000 to 100,000. Some machine learning algorithms are sensitive to the difference. MinMaxScaler transforms each feature into a selected range, commonly 0 to 1. We feed the scaler using only the training data. The scaler learns the minimum and the maximum values from the training set. We then transform both the trainings and the testing feature using the learned values. Notice that we call feed transform on the training data, but only transform on the test data. This prevents the test to set influencing the pre-processing process. The scaling changes the numerical representation, but it does not automatically fix incorrect values or outliers. An outlier is an observation that differs substantially from most other values. Outliers can affect average visualization, feeder regression lines, and model performance. However, one outlier should not be removed simply because it looks unusual. It might be a data entry mistake. It might represent a measurement problem. It might also be a rare but completely valid case. Before removing an outlier, investigate its source and meaning. Outlier detection methods identifies values that deserve attention. They do not automatically determine whenever those values are wrong. This distinction is important for responsible data analysis. One method for identifying possible outliers is called Tukey Fences. We first calculate the first quartile, called the Q1, and the third quartile, called Q3. The intercalate range of IQR is Q3 minus Q1. We then calculate a lower fence by subtracting 1.5 times the EQR from Q1. The upper fence is Q3 plus 1.5 times the IQR. Values outside those fences are flagged as possible outliers. This method is closely related to how outliers are often displayed in a box plot. Because it's based on quartiles, it is less influenced by extreme values than a method based entirely on the mean. The flagged rows will still be examined before deciding whenever to remove them. Another method is the Z-score. The Z-score tells us how many standard deviation a value is below the mean. We subtract the mean from the value and divide the result by the standard deviation. A positive Z-score means the value is above the mean. A negative Z-score means it is below the mean. And commonly guided flag values with Z-score below -3 or above +3. This method works best when the data distribution makes the mean and the standard deviation meaningful. It might be less appropriate for heavily skewed data. Like Tukey Fences, the Z-score identifies values for investigation. It should not be treated as automatic instruction to delete records. Let's bring everything together. We begin by loading or generating a dataset. We spend the feature, target, shape, meaning, and quality of the data. We clean missing values and duplicates when appropriate. We identify X, the input features, and the Y, the target. Next, we split the data into training and testing sets. Any pre-processing values should be learned from the training data and they apply it to the test data. We create a model and fit using the training set. We make predictions using the testing features. Then we evaluate those predictions against the actual testing targets. If the model and pre-processing steps need to be reused, we can save them carefully for later use. As you practice this week, avoid several common mistakes. Don't evaluate the model only on its training data. Do not allow test data to influence training or pre-processing. Do not remove missing values, duplicates, or outliers without understanding them. Do not assume that a single high score proves that a model is useful or fair. The most important lesson from this chapter is that Scikit-learn makes a model implementation accessible, but successful machine learning still depends on thoughtful data preparation, correct evaluation, and responsible interpretation. For week 5, complete the assignment reading, watch the lecture for demonstration materials, finish the guidance practice, and complete the independent practice assessment. In the next chapter, we'll be ready to study linear regression in a greater depth and examine how it models relationship between features and numerical targets.